about. So what we saw in the lecture before was for a quasi-realistic kind of computation that could be of relevance for inflationary perturbations in the real world, even in de Sitter space and so on. But for a problem where the bulk calculation looks kind of not trivial to write down, but is fairly non-trivial, we started sort of developing this point of view that we should be able to determine the answer purely from some kind of questions that you can ask, just restricted to the boundary at future infinity. But again, this was very much along the lines of the story with scattering amplitudes at 4-point level, where you use singularities, the symmetries and the singularities, to determine what the answer can look like. And that's what I like to call, being a good, in America, being a good Boy Scout or a good Girl Guide. You're being very responsible. You're doing very responsible things. You exploit symmetries, singularities, very responsible. It's a very good idea to be responsible. If you attempt to keep going that way in the context of amplitudes, though, you go to higher points, 5 points, 6 points, higher points, this strategy of just write down the most general answer and then impose consistency conditions on it, that gets increasingly cumbersome. And as I was saying in the very first lecture, what we've been seeing over the past 10 years or so is a kind of opposite point of view about these things, not where you impose those conditions directly. So that's the responsible thing. Very nice, right? We don't have to talk about time evolution or Feynman diagrams or de Sitter computations the way we did. We can just sort of impose consistency conditions and look at properties directly of the physical object. But what we've been seeing is something more, sort of one step beyond that. The opposite of that, in a sense. We've found new kinds of mathematical structures, new kinds of questions, new kinds of objects, that if you ask the right kind of question of them, the answer they produce, they depend on exactly the same data, but the answer they produce is the scattering amplitude for gluons, and n equals 4 super Yang-Mills, or for phi cube theory, or the nonlinear sigma model, any number of dimensions, and more extensions of that. So what we'd like to do is begin to see that in the context of cosmology, where if any of the philosophy that I was telling you about in the first lecture is on the right track at all, we should see more of this. The closer we get to physics where time evolution matters a lot, we should see more, not less of this. So that's what I'd like to talk about in this lecture, are the sort of first indication for something like this. By the middle of the lecture, we won't do it to begin with, but at the middle of the lecture, after I introduce you to how to do some of these computations, so we get more data, we get a feeling of the kinds of functions we're supposed to be getting, I'll stop and we'll have a discussion. I'll define an interesting class of polytopes. And you'll see their definition, nothing in their definition looks like it has anything to do with time or cosmology or anything. Very natural, simple set of definitions. And then we'll see that when we ask a particular kind of questions about that polytope, the answer is exactly the cosmological wave function. And as we'll see, these polytopes, even though in their definition there's no graph, they're naturally associated with a graph. And the answer to this particular question we'll ask about the polytope will be the contribution of the wave function of the universe associated with that graph. Okay? So that's what I want to tell you about. I won't be able to tell you everything about it, of course, but what I'd like to do, just so we do something concrete, the first part of the talk, I just want to do some calculations for the wave function in a particularly simple class of models. And this is a class of models that we're going to be talking about. And in fact, it's even slightly more general than cosmology, okay? But the class of models I'm going to talk about is we have a conformally coupled scalar. Okay, so in any FRW, it could be, well, let's start off with something cosmological. It can be anything FRW, but the scalar is conformally coupled. Its mass is scalar with conformal coupling to curvature. So that means that after I do the conformal transformation to get rid of the coupling, and I've gone to some new conformal coordinates, to begin with, the action is just some integral d eta d phi squared. In other words, the fact that it's conformal means that the kinetic term is as if it was in flat space. Okay? But I'm going to have the interactions depend on eta. And for simplicity, I'm only going to talk about polynomial interactions here with no derivatives. Okay, but this is in fact the class of questions that we're going to talk about. Completely generic. I mean, we have spatial translational invariance. Although we could even be talking about quantum mechanics, but in general, we could be in any number of dimensions here, any number of spatial dimensions. But we're going to allow totally time-dependent coupling constants. And we're going to do the same thing. We're going to calculate the wave function of the universe at eta equals 0 by exactly the same rules. When this comes from cosmology, these g of etas are a particular power of the scale factor. Okay, so when it comes from cosmology, the powers of eta are the dimension minus 4. For example, if I'm in 4 dimensions. Okay, but let's just leave it totally generic. At the very end, I'll come back and talk about the special case of de Sitter space. Okay, so this is the general problem that we want to solve. Okay, so now let's just get some practice by first going back to flat space and doing something that I promised. So this is flat space, but also time-independent couplings. And so let's just talk about g phi cubed theory. And so we want to compute the contributions to the wave function. We've already done this one, which was the integral d eta. And I'm going to be sloppy about the i's and the couplings in this whole lecture, okay? But we have E1 plus E2. Well, these e's are the magnitude of k, right? But I'll write it like this. So this is 1 over E1 plus E2 plus E3. We saw that already. But now let's go to the next. Let's compute this diagram. This is one that we sweated so much with in the last lecture when this was a generic mass particle, but not in this context. Let's just do this little calculation just to see what it looks like. So I have an integral d eta prime, e to the I, E1 plus E2. So let me call that E12, which is E1 plus E2. Eta, e to the I, E34, eta prime. Can you guys see, am I writing big enough? And I have the Green's function, which if you remember was 1 over 2 E intermediate, and it was our favorite expression, theta of eta minus eta prime, e to the I, E intermediate, eta prime, e to the minus I intermediate eta, plus swapping eta and eta prime, minus e to the I intermediate eta. Okay, so let's do this. Let's just compute this. Let's first look at this term, the term with theta of eta minus eta prime. Okay, that theta is telling us, so here's 0. So eta is running, eta itself is running from minus infinity to 0, and this says that eta prime is earlier than eta. Okay, so to do the calculation, let me just change variables. So eta prime is equal to eta plus, I don't know, let's call it sigma, where now sigma also runs from 0 to minus infinity. Okay? Then, now the integrals are just over eta and sigma, both from minus infinity from minus infinity to 0. The eta, the sigma, and now let's just collect what the powers are. So there's a 1 over 2 intermediate in front of the whole thing. And the powers are e to the I get an e. From here I have an E12, and then from here I have an from here I have an E12. From here I have an E34, and then here they cancel. So I just get E12 plus E34 for eta. Sorry, for the coefficient of eta. What about the coefficient of sigma? It's e to the I. So for sigma, only the eta prime terms matter, so it's E34 plus E intermediate. And therefore, the final answer for this is 1 over 2 E intermediate, always sitting out in front, 1 over E12 plus E34, 1 over E intermediate plus E34. Okay? So, let's now write down the full answer. So we have 1 over 2 intermediate. The terms that we have already are 1 over E12 plus E34, 1 over E intermediate plus E34. Now the other term is going to be the same, just swapping 1, 2, and 3, 4. So it'll still be E12 plus E34, 1 over E intermediate plus E12. And finally, we have the minus term. The minus term is really easy because there's no thetas, right? So it's just e to the I, E intermediate plus E12, e to the I intermediate plus E34. So we just get minus 1 over E intermediate plus E12, 1 over E intermediate plus E34. Okay, so that's the full answer. So you see it's a sum of 3 terms. It's a sum of 3 terms because the propagator had 3 terms in it. But you know that the answer has to simplify. Okay, one reason it has to simplify is every one of these terms, I mean, we can just do it, but also every one of these terms has a pole as E intermediate goes to 0. Okay, but the whole answer definitely does not have any pole as E intermediate goes to 0. The reason is that as E intermediate goes to, E intermediate goes to 0, this the whole Green's function actually vanishes in the limit as E intermediate goes to 0. So the full thing is going to bound to cancel out in that limit. So this answer has to simplify, but let's see what it simplifies to. It's just 1 over 2 E intermediate. I can combine all the poles together. 1 over E12 plus E34, E12 plus E intermediate, E34 plus E intermediate. And so upstairs I have E12 plus E intermediate plus E34 plus E intermediate minus E12 plus E34. So these things cancel. I have 2 intermediate, 2 E intermediate, which cancels this one, and so I'm finally left with this beautiful simple expression, 1 over, and let me now write it back out again, E1 plus E2 plus E3 plus E4. 1 over E1 plus E2 plus E intermediate, E3 plus E4 plus E intermediate. So that's our final answer, okay? So that's our first real calculation of or simple calculation of a piece of the wave function. That's the 5 to the 4 piece of the wave function. Now, with this explicit answer, let's just check out some things that I promised you. So I told you that the answer has a pole. I told you in general to expect that there should be a singularity when the sum of all the energies goes to 0, and that when you sit on that pole, the residue on that pole should be the flat space S matrix. Okay? So let's see how that happens. I mean, here I just have some energies. There's nothing that looks like S minus M squared, which is what I would, or just 1 over S, which is what I might expect to see. But let's see how it happens. You see, when E1 plus E2 is equal to minus E3 minus E4 on the residue of that pole, so when E1 plus E4 goes to 0, the residue is just 1 over E1 plus E2 plus E intermediate times negative E1 plus E2 plus E intermediate, which quite beautifully is 1 over E1 plus E2 squared minus E intermediate squared, which is indeed equal to 1 over S minus M squared. Okay? So we see how the flat space scattering amplitude indeed emerges as the residue of the pole on the thing. I guess in what I did, the particle was massless, so I would just call that 1 over S. Okay? Any questions about this? All right, so now let's proceed and solve our general problem. At least set up our general problem. So what we want to do is solve the problem with the totally general time dependence. So first of all, what I'm going to do is, actually, maybe before getting to, well, we'll do it all in one step. So now we want to do the general problem. And what I'm going to do is Fourier represent all those coupling constants, all those GA of eta that we're talking about, GI of eta. I'm going to write them as some integral d energy, e to the I epsilon of eta times some g tilde I of epsilon. Okay? And so then we'll just bring, so whenever we're doing, when we look at our, therefore when we look at our Feynman diagram, so let's say I go back to an example like this. Now there might be some general, maybe there's a quartic coupling there too, maybe there's something else. At all these vertices now, I'm going to have a factor. I'm going to pull out all the integrals over the epsilons associated with each vertex. Okay, so and so here on each one of these vertices, I'll have some e to the I epsilon eta associated with that each vertex. So each vertex has its epsilon. That's the time dependence, and there'll be an e to the I epsilon associated with that vertex. Okay. Later, we'll do the integrals over epsilons, but what we're going to do is do all the time integrals first, right? That's the thing that we want to do. So each vertex gets an extra factor of e to the I epsilon. Now, notice in these pictures that all the propagators that go out, all of them that come to a point, it's kind of pointless to keep track of all of them because all you do is add up all their energies, right? So here, there'd be some, so, you know, here there's some e to the I E1 eta, there's some e to the I E2 eta, but all of these things add up just to some overall, energy here, right? So whatever the sums of all the energies were that ended on that, I might as well delete all of the lines going out to it, okay? And I'll just remember what the total energies were associated with all the lines ending on that. So here there would be some E1 plus E2, and of course there's a plus E from the vertex. Okay, but at the end of the day, there's just some e to the I, something eta associated with each vertex. Okay? And so in this way, we can prune the graphs. We can prune the graphs so that everything going out to the boundaries isn't there anymore. So for example, for instance, instead of this graph, I would draw this. Okay, I would just draw that. Okay, and so there's energies associated with each one of these vertices, and there's energies associated with each one of the internal lines, right? The magnitude of the K intermediate associated with each internal line. So our new, our slightly pruned diagrams, or then you just draw any old graph. So let's say, let me draw a more reasonable one. So this thing would be this graph. Okay. This thing, right, that would be this graph. That would be this graph. And I can draw loops as well, right? So for example, this thing, that would just be this graph. Okay? When I have internal loops, I have to integrate over the spatial momenta. I'm going to do that later, right? So what I'm doing now is just doing all the time integrals. I want to figure out how to do all the time integrals. Later, we'll convolve with the product of all the g tildes for all the vertices. We'll integrate over the spatial loop momenta, but I'm taking care of the time-dependent part of the problem. Is that clear? So So what we now have is a function associated with a graph. You give me any old graph. For any graph G, there's a function, and I'm going to clean up notation a little bit. I will denote the energy variables associated with the vertices by x's and by the edges as y's. Okay? Instead of calling them E intermediate and so on, I'll just call them x's and y's. And so what I have is a function associated with any old graph that depends on the x's and y's, the x's of the vertices, the y's of the edges, which is nothing other than integral minus infinity to 0, the product over all the vertices, d eta vertex, e to the I x vertex, eta vertex, and then a product over all the edges of 1 over 2y edge times that propagator, right? Times g of y edge and eta prime. I guess that was part of what I called G before, but all right, anyway. This times the theta of eta minus eta prime, e to the I y edge eta prime, e to the minus I y edge eta, plus eta to eta prime, minus e to the I y edge eta prime. All right, I hope that's clear. Yeah. You can't see it? All right, so let me write this. Yeah, this is important. So let me write the whole thing bigger. This is defining the object that we're going to talk about for the rest of the lecture. Sorry? No. It's all gone. Okay, so I draw any graph, any kind of valency, right? Because we're talking about totally general polynomial interactions. Okay, so associated with any graph, there's f of any graph. Depends on the x of the vertices. Can you see this? Okay, and this is just defined to be the integral minus infinity to 0, d eta product over the vertices, d eta vertex, e to the I x vertex, eta vertex, then a product over the edges of 1 over 2y edge, theta of eta v minus eta prime v minus eta v prime. These are the vertices of the edge. All the vertices, the vertices at the end of the edge, e to the I eta prime, e to the I eta v prime, y edge, e to the minus I eta v y edge, plus theta eta v prime minus eta v. And so this is all the edges E that connect V and V prime. All right? Is that clear? Now, if we compute that object for any graph, we're done with the time part of the problem. Okay? If there's loops, we have to integrate over the spatial loop momenta. We have to integrate over the G tildes to get the final answer, but again, we've taken care of the time part of the problem. Sorry? No, what I said is that I was dealing with a conformally coupled scalar in the free limit. So the kinetic term is time independent, but I'm allowing completely generic time dependence for everything else. Okay? So that's really for the simplicity of the kinetic term being easy. Okay? But in fact, it's even more general than cosmology, because cosmology forces all these g of etas to be a power of the scale factor. Here I'm really doing a completely generic time-dependent problem. Okay? So they should really be called time polytopes, but that sounds even weirder than cosmological ones. So, okay. Now, let me just tell you, so let me just, I won't do any more explicit calculations, but just a little, let me just give you some data, what the answers look like in some simple cases. Okay, so if I just have one vertex, right, that's just the thing that's, so there's just an x, and the answer is just 1 over x. Okay? If I have, this is the one we just worked out, x1, x2, and y, the answer is 1 over x1 plus x2, x1 plus y, x2 plus y. And remember, we got this from 3 terms. But the 3 terms collapse to give me something like that. Now let me give you the answer for this guy. So this is x1, x2, x3, and y1, y2. Now there are 9 terms. And you see, you get the idea that despite the fact that we're just calculating stupid tree diagrams here, never mind anything else, that it's much more complicated than it is for flat space amplitudes. The reason is each propagator has 3 terms in it. So there's of order 3 to the, if there's e edges, of order 3 to the e terms. So already here we have 9 terms. Okay? The same diagram, if it was for an amplitude, I'd just write down the product of one of the propagators, and I'm done. Okay? But because of the physics of time here, we're talking about the wave function and not the amplitude, it's much more complicated, right? There's many, many more terms. And yet, what you find when you do the calculations is that there's intricate cancellations, and the final result is vastly simpler than you would expect. Okay? So, what is the answer for this guy? It's simply x1 plus x3, but it has an interesting numerator now, plus 2x2 plus y1 plus y2, and it has a funny, unusual pattern of poles, x1 plus y1, x3 plus y2, x2 plus y1 plus y2, x1 plus x2 plus y2, x3 plus x2 plus y1. x1 plus x2 plus x3. Okay, anyway, it's something that has that many poles and a very simple numerator like that. I don't know why it doesn't look right here, but anyway, all these 9 terms cancel to something extremely simple. There's this pole in the sum of the energies, and you can, if you work it out, you can see that on the residue of that pole, again, it turns into the product of 1 over the s's. Okay, so again, becomes what you expect from the scattering amplitude. All right, one more. Let's look at a loop. And here there's actually 7 terms. The reason is that some of the time orderings aren't allowed because I have a closed loop. Okay, so 2 of the time orderings give me nothing because the theta functions cancel out, but I still get something extremely simple. I still get x1 plus x2 plus y1 plus y2, and again, a product of a bunch of poles. Let me not waste time writing it down, okay, but it's something extremely simple. All right. Actually, I have them correctly here. It's fine. All right. Okay, so the first thing I want to do is explain where these simple formulas come from. Okay? Well, at least these formulas should remind you of something. Do these formulas remind you guys of anything? Where have you seen expressions like this formula, expressions like this before? 1 over the sum of a bunch of energies and denominators, adding them up. Do you have some dim memory of expressions like this? There's a name associated with formulas of this sort. Something before Feynman. The reason Feynman's famous, he replaced something. Old-fashioned perturbation theory. Okay? Old-fashioned perturbation theory in quantum mechanics is something that gives you formulas that involve sums over energy denominators with sums of a lot of energies. So in fact, these shorter expressions are exactly directly what you get from old-fashioned perturbation theory. But I'm not going to make you go back through old-fashioned perturbation theory because we're actually going to derive it directly from our usual path integral picture, or just from the integral that we wrote down, which is the same thing. And you'll see there's some beautiful systematics to old-fashioned perturbation theory. It's a small irony that at least eventually everything has a lot of graphs, but at low orders, while Feynman diagrams kick the pants of old-fashioned perturbation theory for scattering amplitudes, they're actually more complicated for calculating the wave function. Okay? That may not be so, maybe not so surprising. All right. So let's see how we can get these expressions directly. And so what I'm going to do is go back to this. So I have this formula, which is the integral, the product of the vertices, the eta vertex, e to the I x vertex, eta vertex, and then the product over the edges of the Green's function, which I'll just leave the whole thing, g of y, and then eta vertex prime. Okay? So this is the function that we're interested in. Now let me define an operator delta, which is just negative I, d by d eta 1 plus d by d eta 2 plus ... All of them. Okay? Now that operator is otherwise known as just total time translation, right? Just uniform time translations for everybody. All right? And so let me look at the following thing. Let me look at the product over I d eta v, and let me look at delta just acting on e to the I x1, e to the I xv, eta v, the product of all of them. Okay, times everything else. Okay? On the one hand, what is this thing? Delta hits this to return just the sum of all the x's acting on the same thing. Right? So on the one hand, this is equal to just x1 plus ... plus xv times f. Okay? On the other hand, I can use integration by parts. I can use integration by parts to move this delta over and hit it on this guy. Okay? So on the other hand, this is equal to the integral product over I d eta v, e to the I xv eta v, and then I have delta hitting the product over all these edges of the Green's function. Okay, now let's think about what this is doing. Now, first of all, why do I say it's equal? One thing that's important is that there's boundary terms, okay? But the boundary terms involve the value of g evaluated at the boundary at eta equals 0. And remember, g was designed to vanish at the boundary at eta equals 0. So the fact that there's no boundary terms here is critically using the fact that the g satisfies the correct boundary conditions for calculating the wave function. So this is just a direct equality. But now this is also very simple, because you see there's the complicated part of g with the theta functions, with the step functions, but that part depends only on the difference between eta minus eta prime. Okay, so that part is actually annihilated by delta. Okay? So in other words, delta acting on g of y, eta and eta prime, is just delta acting on the piece which is 1 over 2 ye e to the I eta plus eta prime, eta vertex plus eta vertex prime, ye, which just beautifully cancels, never mind the factor of 2, it just beautifully cancels the factor of ye and just leaves me with e to the I eta v ye, e to the I eta v prime ye. Okay? So what is the effect of this delta? So what is delta doing? Let me illustrate it with a diagram. So let's say we're talking about this diagram. Okay? So what's happening here when, or even let's say, let me draw a more complicated one. Okay? What's happening when delta hits this thing? First, delta is a linear operator. So there's a piece where delta hits this guy and it leaves these alone. Then when it hits that one, it leaves these alone, and so on. Okay? But when delta hits this propagator, then what it's doing is completely removing any of the couplings between eta and eta prime. Okay? And so it's as if you erase this propagator. That propagator is gone. But now I have an extra piece in the energy associated with the vertex of the two guys that it attached to. So if beforehand here I had x1, x2, x3, x4, then after delta hits that propagator, I'm left with x1 plus y, whatever the y was here, and this guy has gone to x4 plus y. And the other guys are left alone. Okay? And therefore, this gives you a simple recursive formula for building F, right? I just, F So F is 1 over the sum of all the energies. Sorry, 1 over the sum of all the x times the sum over all the ways of cutting, of removing an edge, so F for some diagram. All the ways of removing an edge where we shift the energy by the y of the vertex. Okay? So let's apply that already to this simple problem that we just talked about. So for instance, this method tells us that this guy is, so that's x1, x2, y, that this is equal to 1 over x1 plus x2 times what I get for just x1 plus y, x2 plus y, which is just 1 over x1 plus x2, 1 over x1 plus y, 1 over x2 plus y. Okay? And so we can keep going in this way. Okay, so if I do this, there's a piece where I lose that edge. The piece where I lose that edge is just, so there's a 1 over x1 plus x2 plus x3 in front of the whole thing. The piece where I lose that edge is 1 over x1 plus y1 times the problem that we just computed a moment ago, where this is x2 plus y1, y2, and x3, plus 1 where I remove that edge. So when I get x1, x2 plus y2, and then 1 over x3 plus y2, and so on. Okay, so that's how you get it as a sum of 2 terms, not 9 terms. Okay? Now, in fact, there's a way of, it's very simple to convince yourself of this. This is really trivial. There's a way of capturing all this in one go, so you don't have to keep doing it recursively. The final answer is a sum that's associated with a bunch of connected subgraphs of the graph. Okay, so let me illustrate. So you circle vertices in the graph in any way you can compatible with the following rule. So let me illustrate, for example, with this one. Okay. First, you put a circle around the whole graph. Then you find any way of breaking it into two connected, two graphs which are each connected, but only separated by one edge. Okay? Then inside each one, you keep going. So you do the same thing. Okay, so like, so in here, I would, inside here, I would further circle this guy and that guy. Okay? Until you're done. And then what you have to write down for each circle, you have to write down 1 over the sum of all the x vertex inside that subgraph. So it's the sum over subgraphs of the x vertex. So for each subgraph, you do the 1 over all the vertices in the subgraph of x vertex plus the sum over all the edges ending on the subgraph. Let me write it big. Okay, so we have that factor, and you see where this comes from, right? You know, that's coming from each cutting. You have to add the y to both sides, and you have to take the product over all the subgraphs. Okay? So it's just that linear denominator factor, and so for one of these ways, for every one of these ways of dividing the graph into connected subgraphs by this rule, you get that factor, and then you just have to sum over all possible connected subgraphs, connected by this rule. Sum over all the pictures of this type. Okay, if I had more time, I'd introduce some nicer notation, but anyway, this is perfectly fine. Yeah, I'm not worrying about the minus sign. Yes, yes. I've long since stopped worrying about the minus signs and the i's and stuff like that. Okay. So, for instance, here there's only 2 sets of subgraphs: the one we drew and another one. And so I just write down. Well, I won't do it, but we just write down. For example, the big one on the outside is just 1 over. If this is x1, x2, x3, y1, y2. I have a factor 1 over x1 plus x2 plus x3. Then I have, from here, I have 1 over x3 plus y2 for this graph, right? That's the only x in it. Y2 ends on it from the outside. Then I have this thing. So that's x1 plus x2 plus y2. Then I have this guy, 1 over x2, and it's ended on by y1 plus y2. And finally, I have this guy, which just has 1 over x1 plus y1. Okay? So I have that plus the other diagram. So this plus 1 and 3, x1 and x3 interchanged. Right? So that's the systematics of old-fashioned perturbation theory. Except we didn't have to go through the usual way anyway. I think there's this. So just like Feynman rules are associated with graphs, old-fashioned perturbation theory is also associated with graphs, but with this funny rule about finding connected subgraphs in this way. Okay, any questions about this? Yes? Yes? Sorry? This one, because this is, I'm talking about this big one here, and the only thing that ending on it is y2 from the outside. Okay? If it's on the inside, it doesn't matter. So you only sum over all the vertices on. You can see how this is just doing the rule that we talked about, right? This is just summarizing the rule that as you went along, you cut one propagator at a time, and you sent the energies attaching to the graphs that it touched. Okay? And this is true tree, loop, everything, right? So it doesn't matter. It is a totally general thing. So for instance, to just give you another example, if I do the loop diagram, then I would have the whole thing. I'd have this one, and that one, say. Okay, so, boy, I got a little ugly looking. I think I need more than one color. Yeah, so if I have a loop diagram, no, yeah, I'll use it. There's x1, x2, y1, y2, then there's there's this guy, there's that guy, that guy, that guy. Okay? So for instance, you get, I would get 1 over x1 plus x2, just for the whole thing. Then from this graph, I get 1 over x1 plus x2 plus 2y2. Okay, because y2 ends on this graph, both from this side and from that side, and I get a factor 1 over x1 plus y2. 1 over x1 plus y1, 1 over x2 plus y1. Okay? All right. Okay. So, what have we seen? We've seen that we have a couple of different representations of the same problem. Okay? We have what you could call a bulk representation. Now, notice I should have emphasized this. You see what's cool about this rule? This rule is a way of writing down the answer. You don't encounter any time integrals again, right? So this is a way you draw a graph. There's no etas in sight, right? And there's this interesting graphical rule about combining energy denominators together, and it gives you the answer. Okay? So we have a bulk representation, which is, essentially coming from the path integral. And this is the representation with integrals over eta. And then we have a boundary representation, which involves these connected subgraphs. And so on, okay? Now, in fact, in a sense, the most ancient, familiar version of holography is exactly the Feynman path integral prescription for calculating a wave function. After all, let's just say we're in flat space, no time dependence, nothing. Before Mr. Feynman, you calculate, let's say, the vacuum wave function, you solve the Schrodinger equation, okay? Done. Then Mr. Feynman comes along and says, no, you can do it another way by imagining a time integral. You've now added a time direction that wasn't there in the problem. You didn't know anything about that, okay? But you represent the same thing as an integral over a bulk time that ends on the point. So in fact, before Feynman, people only knew about the boundary way, okay? And then after Feynman, there's a boundary way, there's a bulk way. And if I had longer, I would tell you more about the virtues and the defects of each one of these descriptions, okay? A few things should be, for example, there's clearly a virtue in the boundary way. The virtue in the boundary way is that the virtue in the boundary way is that only the poles that show up in the final answer show up in each piece of the boundary, okay? Whereas the bulk representation has lots of those spurious poles that cancel only when you do the sum. The virtues of the bulk representation are actually a little harder to explain. It doesn't have all that many virtues, but it has some, of course, that are related to Lorentz invariance ultimately. But anyway, if I had longer, I would explain a little more. But in any case, this is already sort of interesting. We have two different representations of the same object, and so each one of them gives us the same final answer, fg of x and y, but via very, very different routes. And so we can ask, is fg of xy, is it somehow the answer to some other question? Right? Is fg of xy the answer to some other natural mathematical question? And if it is, can we, from that question, then understand why it has the features that lead us to be able to represent it from a bulk time integral point of view or from a boundary point of view? Okay? So, is the question that we're now asking clear? Any questions? Yes? Quick rotate, you can quick rotate. This question has been asked a number of times, and we might get there, although probably not. But of course, if you can rotate, you can rotate. However, when we see the final geometrical object, you'll see that, so there's some, let me just say it right now, there's some polytope, okay? I'm going to define a cosmological polytope, and there's a certain canonical form that goes along with these polytopes that has a property that it has simple pole singularities on all the boundaries of the polytope of all codimension. That's called the canonical form that goes along with the polytope. This canonical form is very closely related to a volume. It's not the volume of the polytope, but the volume of the dual of the polytope. Okay, so that's just what I was going to give you a little crash course on in a moment here. But anyway, so there is some object here, and I'll give the polytope some intrinsic definition. We'll forget about all this, and I'll just define an interesting class of polytopes. Happens not to have been defined by mathematicians before, but it's a very simple natural class of polytopes. So, now, one thing that we've seen in the story of scattering amplitudes is not just the polytope itself, but all of its faces mean something, okay? And the facets are associated with certain kinds of singularities of the object. You can ask in this context what the residues on the poles mean, and they're associated with particle production when you have time dependence. Okay? So if you don't have actual time dependence, you never have access to that. So that's why you could do all of these things in Euclidean space for the full answer, no problem. But then, from that point of view, discover, oh, interesting, if I allow it to be Lorentzian, then the things on the boundaries mean something, and they're associated with the weights for particle production. Okay? So that's why, despite the fact that they're all rotatable to each other, I feel it somehow cares about time. Okay? All right, so now, before jumping to define the cosmological polytopes, in order for you to get anything out of this, what I want to do is perhaps help also remove some of the barrier to thinking about some of these things. So in this kind of connection between geometries and physics of this form involving polytopes or more general objects that we call positive geometries, the kinds of geometric questions and the things that you do with it are not typically what we teach physics graduate students. Okay, so, but the subject is incredibly simple. It's much simpler than, I mean, it's simpler even than, you know, freshman calculus. Most of what goes on in this, it's all projective geometry. You can explain most of it to smart high school students, okay? So the only problem is that it's slightly unfamiliar. So I want to just spend a few minutes, maybe just 15 minutes, on a crash course on projective space, projective geometry, what it's good for, just so you see how easy it is and to encourage you to play with it. And then after we see some of those things, I'll move on to define the cosmological polytopes and at least give some of the claims. I think given the time, I'm not going to be able to do much more. Okay, but let me just first give some motivation for going to a projective. Of course, projective space is a very important thing that doesn't need any external motivation. But let me just start for a second and talk about polytopes, or even polygons for a second. Okay, so let's say I want to talk about points on the inside of a polygon. So the usual way of thinking about this is that any point on the inside is a weighted sum of the points on the outside. Okay? So if the points on the outside are Z1, I'll just put a vector index on them up to Zn. Then we'd say that any point on the inside, Y, is W1 Z1 plus Wn Zn. Yes, that's the definition of the convex hull. Okay, this is the definition of the convex hull of a bunch of points. Okay, now, already here, there's something that motivates you to think about projective space, because that 1 over W1 plus Wn is a little ugly. So what we're going to do is add one variable. So we're going to add one variable, one dimension, and think about this two-dimensional space as really P2, okay, the two-dimensional projective space. So we're going to have three-dimensional vectors modulo overall rescaling. All right? So I have three-dimensional vectors. Yi runs from 1 to 3 in this case. Okay, and it's modulo overall rescaling. So, for example, if I can always rescale, say, to put the top guy to the form 1, then I have one little, let's say, little y down here. And then, you see, my formula becomes nicer. It's that just yi is W1 Z1 plus Wn Zn. Okay? With the w's positive. Sorry, it's very important here that the w's are positive. And so what we're really doing here is looking at a whole cone, right? So here's the direction Z1, the direction Z2, the direction Z3, the direction Z4. Okay, we're looking at a whole cone that's spanned by all those directions. Now these are the three vectors, Z1 up to Zn. And it's a usual picture of how you think about projective space, a space of all lines passing through a point. In that space, there's this cone, right? The set of all lines that actually lie inside this cone. And now I can choose some plane at infinity, right? I can choose some plane at infinity, just some way of chopping this, and that'll give me a picture that'll take me back to this picture, the picture of the actual polygon that lives in 2 dimensions, okay? So these are projective polytopes. And in one direction, if you're given any sort of normal picture of a polytope like this, of course, you can always lift it to one higher dimension and think of it projectively in this way. The opposite is not always true. So let's say I go the other way. Someone hands me a bunch of z's, and I write down this formula. Does this mean that I have a polytope? Not necessarily. It's very important that this formula is projectively well defined. What that means is that the left-hand side should never be able to go to 0. Okay? And well, let's see why. The left-hand side never being able to go to 0 means that there should be some hyperplane that on which side all the z's are on the same side. Okay? So this is good, because all the z's are on the same side of this hyperplane, right? Whereas, and that's what we're doing when we put the top component to 1. Right? When we put the top component to 1, we're exactly saying there's that hyperplane that we call the hyperplane at infinity, and everyone's on the same side. This would be bad, right? So if I had something like this, then this is bad because it's possible with these vectors to make a basis and you can get everything. You cover all of Y space, okay? So there is not actually a sort of compact region associated with it. Okay? But in all the cases that we're talking about, we'll be in a situation where this condition is satisfied. Okay, so this map needs to be projectively well defined, but then everything is fine. Now, let me just say a few things about projective space in general. And you should really learn to think projectively, regardless of anything I'm telling you, because for every geometry problem you'll ever run into, where distances don't matter, and there are many, many problems like that, it is really a bad idea to think in Euclidean or Cartesian terms. You're just dragging around some metric structure that doesn't need to be there, and it very often obscures formulas, it obscures seeing what is going on. Okay? In a projective space, so I'm going to have points. So these yi, let's say in a general, if I'm in Pn, I will run from 1 to n plus 1. Okay? I have to identify y with ty. Okay? That's what makes it projective. Okay. And the only symmetry that I have, there's no metric, nothing. The only symmetry I have is GLN. Okay? Just all about vectors, or GLN plus 1, because it's an n plus 1 dimensional vector. The only invariant tensor I have is the epsilon symbol. Okay? And so the only kind of invariants that I can write down are contracting things with epsilon symbols, which I'll always denote by putting things in brackets. So I can have like Z1, Z2, Z3, for example. Okay, so this means that something, I'm always contracting them with the epsilon symbol. All right, so what are some things that this is good for? Well, so points y upstairs I, these are points. Now, let's look at an equation of the form w downstairs I, y upstairs I equals 0. Okay? What are all the y's that satisfy that equation? All the y's that satisfy that equation for a fixed w lie on a hyperplane, right? So a w with a lower index is actually associated with a hyperplane, right? So these are points. W with a downstairs index could be a plane. So let's just do some simple exercises here, right? So just even in P2. So let's say I hand you a point 1 and a point 2. So coordinates Z1 and coordinates Z2. And let's say I want to know what is the line that connects the two of them. Okay, well, if you go back to elementary school, you would write down ax plus b, and you'd make sure that it passes one through the other, and so on. Okay? However, here it's much, much simpler. Because all you have to do in projective geometry is take the objects that you're given and put them together in the only way you possibly can so the indices come out right. Right? So what is the line? What is the line? Well, somehow I have to take 1 and 2, and I have to make something from it with a downstairs index. Well, so there's the line L12 with a lower index, which is just epsilon ijk, Z1j, Z2k. Okay, so that's the line. And we can check that the points are on the line, because clearly L12i, Z1i is equal to 0, or Z12i is equal to 0 because I contract Z1 or Z2 with itself, with the epsilon symbol. Okay? All right, so that's pretty simple. What about the other way? What if someone hands you 2 lines and you want to know what point they intersect at? Exactly the same thing. Okay, you just write down the 2 lines and you intersect to get a point. Okay, what if you want to know? Anyway, we can of course do this. What if we're in 3 dimensions? Okay, if we're in 3 dimensions, what if I have a line and a plane? Okay, so what is a line? A line is in 3 dimensions is an antisymmetric tensor with 2 downstairs indices. Okay. Oh, sorry. It's an antisymmetric tensor with 2 upstairs indices, although here they happen to be dual to each other. What is a plane? A plane is something with a downstairs index. So what is the point where the line intersects the plane? Well, we just wrote it down. That's the intersection point. Okay. Okay, this might not impress you so much. Well, none of it's very impressive, but it just shows you how simple it is to think in these things and actually how useful it is. Let's do another quick exercise. Let's say I have a conic. So let's say I'm back on a plane and I have a conic. Now, what is a conic? A conic is something that has an equation of the form Qij, Yi, Yj equals 0. So a conic is a symmetric tensor. Okay? It's symmetric in I and j. Okay? So let's say I give you a conic. So I've given you some Qij. Let's say I give you a point on the conic. So I'm telling you there's a point on the conic, which is some x star upstairs I. Okay? So what is the tangent to the conic at the point? Only thing you can do, it's a line, so you contract q with x, and that's it. So this tangent is qx with a downstairs index. Okay? And so on. So I encourage you to play, you can play all kinds of fun games. Let me give you a final example. Let's say you have a conic again, and you have a point here, x. Okay? Sorry, and you have a conic, and now you have a line. Then with a conic and a line, you can also build a point. And which point do you think it is? With a conic and a line, you can build a point, and the point it is this point, the intersection of the tangents of the two lines with the intersection points. Okay? Right? So it's trivial. It makes geometry trivial. Okay? Everything that does not involve Euclidean distances, conics, cubics, anything you want to do. Okay? And it reduces everything to linear algebra. Right? So that's the... And as I said, this is an ancient, simple subject. It's much simpler than all the things that we teach kids very early in life. These things were done by people in the 14 and 1500s. Well, not the business with the epsilon symbols. But by the way, final thing, there's obviously a trivial way of changing upstairs indices to down and downstairs indices to up, and nothing changes. And that's the famous projective point-plane duality. Okay, so if you have any statements that's true about some configurations of lines, points, planes, exactly the same statement is true if you reverse everything. Okay? All right, so that's a little crash course on projective geometry. Now let's talk about some very familiar notions in this language. Now, the whole point in projective geometry is that everything is everything we have to, it should be invariant under rescaling. So, for instance, we can't have something like in order to talk about the notion of something like an area, forget about distance, okay? We can talk about something like a notion of an area, but only up to overall rescaling. Okay? So what we normally call like the area of a triangle, for example, that's something that we can talk about projectively, but in order to do it, we need to make a choice of who is the line at infinity. Okay? Once we make a choice of a line at infinity, or hyperplane infinity, then we can have a useful notion of an area. Just to show this concretely, many of you remember this formula for the area of a triangle whose vertices are x1, x2, and x3 on the plane from school. And this is a half this determinant, 1, x1, 1, x2, 1, x3. Okay? So you remember this? This is like x1 minus x2 cross x3. Okay? But this is really a projective formula, right? So let's, so this area is actually 1 over x1 dot y, x2 dot y, x3 dot y, where this dot means lowercase I, uppercase I. And upstairs, we have to contract x1, x2, x3 in order for this to be invariant under rescaling 1, 2, and 3. Okay? So this is something that's projectively well defined. So let me just write it a little more cleanly again, I could just x1, x2, x3 over x1, y, x2y, x3y. This is the area of a triangle. To reproduce what we talked about before, I choose the line at infinity to be y with the lower index to be 1, 0, 0. I choose x with the upper index to be 1, little x. And then this is exactly, this returns the previous formula, because all these x dot y's become 1. Okay? Now what else? What about on the plane? Again, remember on the plane, without any notion of distance, I definitely have an invariant metric, right? I can just write down dx wedge dy on the plane. So what is dx dy as a projective idea? Dx dy, I have to write this. So now if I write, if my coordinates are, maybe I should have called this w because it's a plane. Sorry, guys. Because y's are almost always going to be points in what I'm writing. I apologize. Okay, this would be w, some plane infinity. Okay, but let's say then what I want to do, just to get a clue, I want to write down y is 1, and let's say xy, little y here. So how do I get this thing out of that? When the only invariant tensor I have at my disposal is the epsilon symbol. Well, it's the only thing it can possibly be. It's y dy dy. Okay, y dy dy all wedged together is exactly the invariant measure on a projective space. Okay. So with all that preparation, we can also do things like talk about differential forms on projective space. For example, on P1, I can have a form that looks like y dy. And in order to make up the weights, I have to have something which has weight 2 in y downstairs. So I could have, for example, yz1, yz2. All right? And this is P1. And if I go back to the homogeneous coordinates, if I say y is like, 1x, say, then this would just be dx. Oh, sorry, and then 1, 2 upstairs. Okay, this would just be dx z2 minus z1 over x minus z2, x minus z1. Okay, so that's the simplest form I could write down. I can keep going. The same thing in 3 dimensions. I can write down y dy dy 1, 2, 3 squared over y z1 z2, y z2 z3, y z3 z1. All right? And again, you see, notice this is a form. This looks like dx over x minus z1 minus dx over x minus z2. Okay, this thing is d log of x minus z1 minus d log of x minus z2. So we say that this is a form that has logarithmic singularities because locally it looks like dx over x. It's a form that has logarithmic singularities on the boundaries of this interval. Okay? It's a complex form, but it's a complex form that's completely determined by telling you that its singularities are located on the boundaries of this real interval. Okay, so similarly, when I go to the next example, this is also a form. You can see this is just, still, it has logarithmic singularities, a bunch of simple poles downstairs. And what is this? It's a pole with logarithmic singularities on the boundaries of a triangle. Triangle whose vertices are z1, z2, and z3. Y is in here somewhere. It doesn't matter where it is. But you see it has poles when y, sorry, I forgot to say this. This is one of the most basic things I should have said when I was giving you the introduction to projective geometry. Hopefully it's obvious. But let's say on the plane, I have 3 points. Okay? What special relationship can those points have to each other? There's no notion of distance. Okay, so what special relation? Nothing. except if they're all collinear, right? So if they're all collinear, what does it mean if they're all collinear? It just means that 1, 2, 3 has gone to 0. Okay? So incidence, I should have mentioned, very important. All incidence relations are just about those determinants vanishing. Okay? And I encourage you to do a little exercise. It's a non-trivial exercise, but you'll really see the power of this way of thinking about things. This exercise was first done over 2,000 years ago by Mr. Pappus. Mr. Pappus, observing olive groves in Greece, planted in rows, observed the following fact, that if you have 3 points that are collinear on this line, another 3 points that are collinear on this line, and you now construct the following set of points. So 1b, 2a, that's some point here. 2c, 3b, that's some point here. And finally, 1c, 3a, at some point here. Mr. Pappus observed that these things are all also collinear to each other. Okay? And it's a nice exercise in playing with determinants to prove Pappus's theorem, right? So that's a completely brainless way of proving it. You just shove the points in, shove it into Mathematica, press Shift-Enter, and you'll find that those 3 points that you get are actually 0, right? Just do it just algebraically, right? Okay, but anyway, so we have, so that means that because when I say there's a pole here, when y, when y1, 2 is 0, it means there's a pole when y hits that line. Okay? But it's actually more than that, because when I go to that line, I can take a residue, right? So it looks locally like dx over x in some variable. I get rid of that variable. Now I'm localized to that line. The form on the line itself has logarithmic singularities on the boundaries. Okay? And so it goes down in that way. So that's what's non-trivial about, so here in these examples it was all trivial, but this is a way in which it's possible to associate geometries with differential forms in a canonical and interesting way. So, for example, just to show you the first non-trivial example. So that's something we call a canonical form. So if you're given a geometry, and in this case with polytopes it's all guaranteed, so I don't need to define what I mean by positive geometry, it's just a polytope. There are more general spaces, Grassmannians, more general spaces in which these kind of objects can live, which need a more careful definition, but here just polytopes are fine. So let's say you're given some convex polytope. Then there's a canonical form, some convex polytope P that lives in some projective space. So we have some convex polytope P. You have a projective space with coordinates y. Then there's a canonical form on y space that depends on the polytope with the property of having log singularities on and only on all the boundaries of P. So we just saw how it works for simplices in general. That's trivial. You just write down 1 over all of the just what we wrote down. But let's look at the first interesting example, which is a quadrilateral. Okay, so let's say we have draw it a little more extreme. Okay. So what could the form be in this case? Well, clearly, it has to have singularities when y hits each one of the lines 1, 2, 2, 3, 3, 4, and 4, 1. Y 1, 2, 2, 3, 3, 4, and 4, 1. There's always this y, dy, dy upstairs. Okay? But now there's a problem. We have to have something extra in y upstairs, because this has weight minus 4 up here and only 3 up there. So I need to have something here that's linear in y. So there has to be some line up here. There's some line, Li, Yi, that I need. Okay, but what should that line be? And now you see what the problem is, because for totally generally, this is guaranteed that this has poles here, there, and there, but I want more than that, right? When I jump, let's say, on 1, 2, I only want to have singularities on 1 and 2, but in fact, there are 2 other places I can in general find singularities. There is this point and that point where the various lines intersect. So for instance, if I sit on the pole 1, 2, so I'm localized to this line 1, 2, I could have singularities here, there, and there in principle. Okay, so I don't want to have any singularities there. I don't want to have any singularities there. So the definition of the posit of this canonical form is that it only has residues, only has singularities on the boundaries of the object and nowhere else. So who should that line be upstairs? Well, it's a very natural choice for that line. That line. Okay? That line puts a 0 precisely on those points, and so it guarantees that there's no residue there. Okay? So in simple cases, you can, in brute force, build these canonical forms. Okay? Given simple enough geometries, you can just find what these numerators are to put the zeros in all the places you need and can get more intricate and interesting. But especially for the case of polytopes, everything is very well understood, and let me tell you a couple of things about how to compute canonical forms. One thing, which sounds quite intuitive, but is slightly non-trivial, it's not that hard to prove, but it's slightly interesting, is that you can compute a canonical form. Well, we know what the canonical form is for a triangle, or an interval triangle, or a simplex. You can compute the canonical form by triangulating P and summing omega for the simplices, for the triangles. Okay, so let's go back to this quadrilateral example. For instance, I can say that I take the canonical form for the triangle 1, 2, 3, plus the canonical form for the triangle 1, 3, 4. And it's quite reasonable that this should work, because this puts logarithmic singularities here, there, and there. This one puts them here, there, and there. This guy in here is spurious. There's no singularities there in the answer, but it should cancel out in the sum between the 2 of them. Okay? So I could do it that way, or I could do it the other way. So this is a method that works. If you manage to triangulate the geometry, you just sum the forms associated with the simplices for the pieces. Okay? Now there's another very nice fact, which we can see already here from our simple example of the triangle. So let me look again at this 1, 2, 3 squared over y1, 2, y2, 3, y3, 1. So the form itself was y d squared y times this. Now I can always canonically factor out the y d squared y, right? Whatever it is, I can always write it as y d squared y. There's some function of weight minus 2 in y and the other variables. Okay, well, this is what it is. But we recognize this formula, right? We saw something very similar to this when we wrote down the area of a triangle. Okay? In fact, this is the area. This is the area. But remember there, in the previous picture, when he had the area, y, I called it w. Y was a plane at infinity, was a line at infinity. Now y is a point. So in fact, it's the area of the dual triangle. Okay? So I start off life with a triangle in Z space. So here's 1, 2, 3. This is Z, Z1, Z2, Z3, and Y is a point. But if I dualize, the Z's are lines. Y is a line. These points are Z1 intersects Z3, Z1, Z2, Z2, Z3. And so the area of the dual triangle is just given by the contraction of these guys, which gives me 1, 2, 3 squared, and then y dot each one of the points. Okay, so that's precisely correct. Right? So this is a general fact. This is a general, and it's a general fact for polytopes, for more general positive geometries. It's one of the mysterious and sort of fascinating aspects of the subject to try to discover what the meaning of these dual geometries is. We've been making some steady progress on that, but it's a multi-year effort. However, for polytopes, it makes perfect sense. And so we have the statement that in any number of dimensions, omega of y associated with a polytope is equal to y dny times the volume of the dual polytope with y as the plane at infinity. Okay? And that means that there's another way of computing the form. You take the polytope, you find its dual, then you triangulate the dual. Okay? And then you just add up the volumes from the different pieces. Okay? So these are two very natural ways of building a canonical form. You can triangulate the polytope, you can triangulate the dual polytope. And there are many other ways. By now we know lots and lots of other ways of computing canonical forms that have nothing to do with triangulations, lots of other interesting methods, but these are two rather simple ones. Okay, can I have 15 minutes, Logan? All right, thank you. I really won't take too much more than that. All right. So now, after all that lightning introduction to these things, what are we going to do? We are going to we're going to work in a pretty big projective space. So it'll be associated with any graph. We'll see how the graph comes about in a second. But associated with any graph, we're going to work in a projective space which is E plus V minus 1 dimensional. Okay, so in other words, we're going to have a big Y, call it a big capital Y, which is an E plus V dimensional vector. Okay, and I'm going to think of this big Y as actually containing all the X's and little y's. Okay, so this is just going to be something that contains all the X vertices and all the Y edges. Right? Okay, so in this big space, we're going to define a polytope. We're going to define a cosmological polytope. P, that's associated with the graph. And omega of P graph and Y will equal Y d E plus V minus 1 Y times exactly the piece of the wave function that we've been just computing associated with the graph that depends on the X's and the Y's. Okay? So this polytope is just going to be something, we'll see it as essentially, it's like has integer coordinates, right? So it's some sort of fixed, some fixed polytope. Y is like the, yeah, so we have so the wave function of the universe, this piece of the wave function is giving you the canonical form with logarithmic singularities on Y. And from what I just told you, we can also identify this as we can also identify this directly as the volume of P cosmological dual with Y playing the role of the plane at infinity. Okay, so we have two dual definitions. And what we'll see is that a natural, we won't see, but I'll tell you a little bit. A natural triangulation of the polytope gives us the bulk. Gives us the bulk time integral representation of the answer. A natural triangulation of the dual polytope gives us the old-fashioned perturbation theory representation of the answer. And then there's zillions of other things that have no standard physical meaning and are far more efficient, in fact. And there's lots of hidden symmetries of these objects that are not manifest in any one of the previous pictures that are seen with the cosmological polytope, and so on, right? But let me just take a few minutes just to define the cosmological polytope. And now let's even forget about graphs altogether, okay? I'll define it, I'll draw you one picture, and then we'll call it a day. We're going to begin with a collection of triangles. We're going to have a collection of triangles. ABC. Okay, so there's some vectors and some abstract vector space. A, B, C. But the triangles are going to, and I can have A1, B1, C1. A2, B2, C2, and so on, okay? To begin with, they're all disjoint. So I just have a whole bunch of disjoint triangles. But now I want to allow the triangles to meet each other. I want to allow the triangles to intersect each other in an interesting way. But there's going to be one funny rule, okay? The one funny rule is that each one of these triangles has an unfriendly side. Let's say the unfriendly side is AB. And two friendly sides. Okay? What that means is that it is allowed to intersect other triangles at the midpoint of these lines on the two friendly sides, but nothing can intersect it on the unfriendly side. That's the only place I'm introducing some asymmetry into this problem. Okay? And that's it. So now, what that means is that if you take, now I allow all the triangles to, now I try to make a picture so they're all connected. Okay, so I don't have any disconnected pieces. So what does this mean? In practice, it means that if I have two triangles intersect, either I can have AI plus CI equals A prime I plus C prime I, or BI plus CI equals B prime I plus C prime I. That's just saying that the midpoints agree, right? Is that clear? They're allowed to touch on the midpoints, but not AI plus BI equals A prime I plus B prime I. So I never allow that relation. Right? So that's it. That's the entire problem. You give me a whole collection of ABCs that satisfy those rules, okay? In some way, such that all the triangles are connected in the end. Now, before telling you anything else, let me just say, this little funny asymmetry should remind you of something. See, there's a 3 in the problem. There's a triangle. There's a 3 with two things being of one sort and one thing being of a different sort. We'll see very concretely that that's exactly the space-time picture. Okay? When you have a picture of space-time, you have a future and past. Those two things are on a similar footing. And then you have space-like, which is different. We also had a 3 in our propagators, if you remember, right? We had the past, future, but the other one was different, had a minus sign, right? Minus the piece that didn't care about the time ordering at all, right? So this little asymmetry in the rules associated with the triangles is where all the physics of time enters the problem. Okay, but we don't see any of that yet. Okay, we're going to see it in studying the object. All right, so in principle, I'm done at this point. Right? In principle, I'm done. All we now have to do is go explore the consequence of what this geometry looks like, compute the canonical forms, and you'll find, but let me now tell you why is this associated with a graph? because of that business with two friendly sides and one unfriendly side, it's actually useful to represent, just abstractly represent, each triangle. So I'm going to represent each triangle with a little dumbbell like this. Okay? What that's doing is this is going to denote the two sides that are friendly, and that's the one side that is unfriendly. Okay? So each triangle is actually associated with a little dumbbell picture like this. And all I'm doing is I'm starting off life with a bunch of disconnected dumbbells. And now what I have to do is glue them to each other along their vertices. Okay? Until I get a connected picture. Well, that's a graph. It's amusing that this is a different way of thinking about a graph than it's a dual way of thinking about a graph than we're maybe mostly used to thinking about. Normally we think about a graph, many of us, as a bunch of vertices connected with edges, and this is the other way around. Okay? This is a bunch of collections of edges that are connected along their vertices. Okay? So in this way we see that the cosmological polytopes are associated with graphs. Now let's actually draw what they look like in various cases. Oh, and I'll do one more thing. I didn't tell you how to interpret what those XY variables were, okay, in terms of this picture. Well, once you have one of these things, I'll draw it like this now. Remember, these things are the vertices of our triangle, but let's say this is the unfriendly side. Then it's reasonable to call this midpoint the unit vector x1, the unit vector x2. I don't want to put hats on them, but they're not scalars, so these are sort of unit vectors. And then on this side, there's a unit vector that I'll call y. Okay? And so if you do that, who are these? And that is x1 plus x2 minus y. This is x1 plus y minus x2. And this is x2 plus y minus x1. All right? And so now I'm done. So now when I tell you that y is to be interpreted, so damn it, if I put hats everywhere here, I don't like putting hats in projective space because there's nothing normalized. But I'm just emphasizing these are vectors. They're like, in some basis, they're just 1, 0, 0, 0. Then what I'm saying is that y is, x1, x1 hat, plus x2, x2 hat, plus so on, okay? The whole big Y that I write for the whole thing is written out as a sum of all these, of all the things on the intersection points. But the polytope is made out of these other things, okay? So in fact, now that, so we started off with this picture of intersecting triangles, but now that we know that it's associated with the graph, we can also just directly, given the graph, say what the polytope is. So given a graph G, associated with any edge, so we have now these vectors, x hat, associated with the vertices, y hat, associated with the edges. With any edge, x hat prime, and y hat, with any edge, there are 3 vertices of the cosmological polytope. There's a triangle associated with every edge, and it's x hat plus x hat prime minus y hat, x hat plus y hat minus x hat prime plus y hat minus x hat. Okay, so this is one of the triangles. All right, so that's it. Given a graph, there is a polytope with 3 times e vertices. That's the cosmological polytope, and it's read off from the graph in this way. Okay, so now I really am done. In principle, from this point on, you can just study and see that the canonical form of this object does exactly what it's supposed to do. But let me give you just a few, one or two examples. So let's do the simple example of just Sorry? I'll tell you in a second, okay? So, first of all, let's just take the simplest case. Okay, so here, let's take the simplest case where my graph is just this thing. So again, I would have some unit vectors, x1 hat, x2 hat, y hat, and so we've just written down what the vertices are, okay? So we have a triangle with those vertices. Now I claim that the canonical form with logarithmic singularities on this triangle is the answer. So let's see. In this case, it's just a triangle. So all I have to do is find what is the line that, what is the line, what's that line, what's that line, what's that line? Okay? Well, so I claim that this line, and I'll introduce the notation in a second, is x dual 1 plus x dual 2. This line is x dual 1 plus y dual. And this line is x dual 2 plus y dual. What these duals are, remember the x's are points, so we want lines, so they're going to have upstairs indices, and the duals are just things that are defined such that they dotted into their guy is 1 and dotted into everyone else is 0. Okay? Now, why do I say that? Well, so I claim that these 2 points are on that line. Well, is it true? When I dot this into here, from x tilde 1, I get 1, and from this I get minus 1. Okay? So that one's on the line, and similarly here, that one's on the line. And similarly for the other ones. Okay? So what is the canonical form? It's y dy dy, but anyway, there's that piece, but then there's over, and then y dot, this one is just the corresponding variables. It's just x1 plus x2, and then x1 plus y, x2 plus y. So that's exactly what the answer was. Okay? Let's draw another picture. The only other one that we can visualize easily, which is three-dimensional. So let's say we have this graph. Okay? The one loop graph. This is now 2 triangles. There's one triangle. There's another triangle, and they're intersecting on both of these midpoints. Okay, so if I draw it, be like this. It's a three-dimensional picture. Okay, so let me draw it better as a three-dimensional picture. It actually looks like this. Looks like a truncated tetrahedron. And in this picture, one triangle is this guy. So this. Where did my chalk go? One triangle is this guy. The other triangle is that guy. You see, they intersect there and there. Okay? Now this is more interesting. Now this is more interesting, and I have to learn to triangulate that guy, which I can do in a variety of ways. But just to give you a quick picture of the other way of thinking about it. Oh, actually, I could have gone back here. There's one more thing I should have done with the triangle. So here we just showed directly that the canonical form of the triangle is the full answer. What is Feynman diagrams, though? Feynman diagrams, in this case, is a rather peculiar triangulation where I take that triangle, and remember, in the Feynman diagrams, every term had a 1 over y in it. So in this language, it means that I'm always adding another singularity, right? So Feynman diagrams actually correspond to something that would put a point on the outside and express this triangle as sum of the sum of two big triangles minus a little triangle. Okay, so the 2 plus and 1 minus is actually a triangulation of that sort. Okay, but let's spend some more time with this example. This example is more interesting. So let me just draw the shape again. Okay, so what is the dual of this shape? Maybe many of you aren't so used to thinking about these things, but this is something that has 6 vertices and 5 faces. So the dual is something that's going to have the other way around, right? It'll have 6 faces and 5 vertices. So its dual actually looks like this. It's something that has, as you can see, it has 5 vertices and 6 faces. And what's remarkable is that if you work out the faces, you find that the faces are let me just write them down. The faces are x1, or x tilde 1 plus x tilde 2 plus 2 y tilde 1. And this is associated exactly with that connected subgraph. Okay, so that's this vertex. This vertex is x1 plus x2, which is all of them. In other words, someone asked the question, and it's a theorem, and it has a slightly cool proof that once you define the cosmological polytope by the intersection of these triangles, that defines the vertices of the polytope. Now, in general, if someone gives you the vertices, it's a non-trivial problem to work out what the faces look like, what the whole facet structure looks like. If someone gives you random vertices, this is a hard problem in the large n limit. It's an exponentially hard problem. That's what's interesting about classes of polytopes that mathematicians understand. What it means by understanding them is that you understand everything about them. You understand the whole facet structure. And so what's interesting is that we understand the entire facet structure of these cosmological polytopes. And the theorem is that the vertices are given as defined, and it turns out that all the faces are associated with connected subgraphs in exactly the way that I defined them. That's not obvious. That should not be totally obvious to you, but it ends up being true. But let me just draw what they look like. Let me just finish drawing what they look like in this case. So I have this guy. Sorry, these are just associated with individual ways with any connected subgraph of the graph. I'm not doing the whole circling and continuing going. Here it's just connected subgraphs and nothing else. Okay, so this one is x1 plus x2 plus 2y2, and this one is x1 plus y1 plus y2. And yes, okay. So this one is here is this one. That connected subgraph. That's that one, and this one here is the bottom one. I don't know why I keep drawing it this way. This one. All right. So that's what the dual cosmological polytope looks like. And then there is a, so this is the last picture I'll draw. drawing in a slightly exaggerated way. Okay, so those are all the points that I defined before, and it's very easy to see that those intersection points up there are the point y1, and this is the point y2. All right. The rest is labeled exactly as I labeled it over there. Okay, now, remember, this is the dual cosmological polytope, so we want the volume of this object. So what's the simplest formula for the volume? So that's that tetrahedron plus that tetrahedron. And that's the two-term formula from old-fashioned perturbation theory. Old-fashioned perturbation theory is nothing other than a straight, nice triangulation of the dual of the cosmological polytope to get the volume. You see, there's many other formulas. I could triangulate another way. I could triangulate the sum of 3 tetrahedra. Okay? That's some different formula. It doesn't have a standard physics name. Okay, but there's a canonical set of simple triangulations that are old-fashioned perturbation theory. What's the bulk? The bulk are sets of triangulations that are forced to use, in this dual, these points, y1 and y2. Okay? Or y tilde 1 and y tilde 2. Right? They're forced to use them. That means that the propagators, those are the 1 over y's in the propagators. I don't have time to explain why this is actually a very natural thing and why that's suggested from the geometry that that's a reasonable thing to do, that there's a canonical plane on which all these y's lie, and it's a natural place to carry out the triangulation. But I just want you to see what the triangulation looks like. So I'm trying to get the volume of this whole big thing. And so the natural way of doing it, there's this big tetrahedron upstairs here, made with these 4 vertices. So that's a top tetrahedron. So that's a plus sign. Then I have the top tetrahedron. And I have a bottom tetrahedron from that one. So that's giving me the volume of the whole thing. But it's too much, right? I have to get rid of this guy. So I can get rid of that guy canonically by I hope it's apparent from the picture, probably not, but this is actually a square. These are all coplanar. So there's a big square pyramid here. There's a big square pyramid. So there's a big square pyramid with all of these guys there. And there's another big square pyramid on the other side. So I have to subtract those 2 big square pyramids and add back the overlap of the 2 that I subtracted. And that's a total of 7 terms. And those 7 terms are exactly the Feynman diagram expansion. Okay? So unfortunately, I've gone on far too long already. So let me leave it at that. If we had a little more time, we could actually see what happens when we started carrying out integrations. Okay? So this is the sort of integrand. Again, it's quite similar to the story of scattering amplitudes, where there's a geometric structure associated with some kind of integrand. Okay? Here there's an integrand that's associated with the canonical form of this cosmological polytope. As I mentioned, there's all sorts of representations that have nothing to do with triangulations that make lots of features of these things manifest that are not so obvious from either of the standard physics representations. If you now go and do the particular case of de Sitter space, if you work out de Sitter space for a phi cube theory, something very simple, in that case, all the integral over g tildes actually just instruct you to integrate over that extra energy, E vertex, that we added to every vertex. So we have these simple rational functions, and then all we're doing is integrating those rational functions from some value to infinity. That gives you polylogarithms. Okay, so the answers in de Sitter space associated with any graph are polylogs, canonically associated with the graphs. Okay? So, in scattering amplitudes, you're used to seeing polylogs at loop level and so on. Here, even simple tree level things, we get polylogs. If you've heard anything about polylogs in the past 5 years, you know that the right way of understanding them is this object called the symbol associated with a polylog. It's kind of something that has all of the information about the singularities in branch cut structure. Now, here I already showed you if you're trying to just do the integrals to get these rational functions, it's pretty complicated already, and the cosmological polytope captures it. If you attempt to flat out do the integrals to get the polylogs, it's a complete nightmare. And in fact, if you actually get the final answer, let's say, for the 4-point function, it's just a few dialogues, it's not a big deal. For the 5-point, just tree level 5-point function, it's just gazillions of trilogues. And it just looks like a hopeless, horrible mess. But in fact, there's a one-line formula for the so-called symbol of that object. And it's one line, even though it leads to many terms, because it's one line that instructs you to sum over a bunch of paths that you can take on the cosmological polytope. Okay? So the cosmological polytope also captures, in one geometric go, all of the branch cut structure and the singularity structure, also of integrated answers in the de Sitter case. So what that's saying is that, you see, I promised you that if we're going to do anything where we try to remove the usual picture, there's no time evolution here, there's certainly no Hilbert space where these wave functions live and so on, it must be that the kind of objects that show up are going to be a little unfamiliar, a little more abstract than we're used to. And this is, I hope, a concrete example of what that might look like. I have no idea if it's generalizable, how deep it is, how important it is. But at the very least, we can see that you can do it. Right? You can begin to play this kind. You can at least have a rough imagination of what the answer could look like. We start with a bunch of intersecting triangles with this funny rule about 2 friendly sides and 1 unfriendly side. And out the other end is something that knows all about the physics of cosmological time and the wave function of the universe, at least in this simple set of examples. Now, in the context of scattering amplitudes, this kind of story has gone much, much further. Okay, I hope very much that something similar will happen for the case of cosmology, beginning with the most unsatisfactory thing of all here at this point, which is, awfully enough, this is a story for individual graphs right now, and there must be a story that actually sums all the graphs together in a larger object. All right, thank you very much for your patience.